So the very last section in chapter 2, 2.8 is called Linear Inequalities in Two Variables. So what you're going to notice with these is these are going to be written in terms of both x and y, and it's going to have either a less than or equal to, a greater than or equal to, or a greater than sign. So you have one of your four inequality signs, and then other than that, you have it written as essentially like a linear equation, but instead of an equal sign, you have an absolute value. So the first thing you should be comfortable doing is deciding whether something's a solution to an inequality. So if you have something like this where you have an x and a y, if I want to see if something's a solution, all I'm going to do is plug in the x and y into the given inequality. So here's our given inequality. So if I put 0 in for x and I put 1 in for y, and I want to see if that's greater than or equal to 5. Well, that's just 0. So I get 3 is greater than or equal to 5. So you have to determine if that's true or not. 3 is not greater than or equal to 5. So we would say that this is not a solution to the inequality. For the next one, we're going to do 2 times 4, because that's your x value, plus 3 times negative 1, and see if that's greater than or equal to 5. So we get 8 plus a negative 3, which is 5, greater than or equal to 5. Well, because it's allowed to be equal to, because of the equal than sign, we would say, yes, this is a solution. And then the last one, we're going to do 2 times 2 for your x value plus 3 times 1 and see if that is greater than or equal to 5. We get 4 plus 3, which is 7, which is definitely greater than or equal to 5. So we have this one as a solution as well. So when you're looking at solutions to linear inequalities, you're going to have a variety of solutions. We're going to say that my solutions cover what's called a half plane or a shaded region of the graph with a boundary line. So there's a couple ways to do these, and I'm going to fill in some key information here. One option, I'm going to call them just method 1 and method 2, is that you're going to graph using intercepts. You're going to do this when it's in this form, when it's in standard form, and you have any inequality symbol. So anytime you are in standard form, you're going to do it by the cover-up method. So you're going to cover up your x's to find your y-intercept. You're going to cover up your y's to find your x-intercept. And then once you do that, you're going to draw your boundary line. And so this is how you tell if it's a dotted or solid boundary line. It's all going to come from the type of inequalities you have. So if you have an inequality that doesn't include the equals to, we're going to put a dotted boundary line. And if you have one that does include the equals to, you're going to put a solid boundary line. And I'm going to show you on Delta Math how to do that as well. And then finally, to determine which side you shade. So when you draw your boundary line, your solutions will either be on one side of the line or the other. And we're going to kind of color it in to show that. We need to use a test point with this. So the test point that is the easiest to use is the origin 0, 0. If it makes it true, you're going to shade that part. If it makes it false, you're going to shade away from 0, 0. And I'll show you an example of this so it makes a lot more sense when you actually see one in action. So that's one option, and that's what I'm going to do if it's in standard form. My next option is if it's in slope-intercept form, or if you get it in slope-intercept form. So when it's in slope-intercept form, you're going to have it in this like y equals mx plus b form. But again, you're going to have a less than sign or a greater than sign, not the equal to sign. You're going to use the y-intercept to start. So you're going to start at your y-intercept. And then you're going to use your slope to determine how I move. So your slope's going to tell me if I go up or down or right or left. And we're going to then shade put my boundary line either as a dotted or solid, again, depending on if you have an equal to or not. And then when you have it in this form, when y is by itself, so when you can get y isolated like this, you don't have to use a test point. Instead, what you're going to do is you're going to shade either below or above, depending on the inequality. If it is a less than sign, you're going to be shading underneath the boundary line. If it's a greater than sign, you're going to be shading above the boundary line. And again, I can show you how all this happens on Delta Math. So here we go. I want to start with some really basic ones, some of the special cases. If it only has a y, this is going to be a horizontal boundary line. So you're going to go to -2 on the y-axis and put a point. So -2, put a point. And then you're going to draw your boundary line horizontally. The other thing you're going to check is because it has a less than sign, not an equal to, you're going to draw a horizontal boundary line. And then you have to decide what color to shade or what side to shade, if you should shade above or below. Well, since this is talking about when y is less than -2, less than -2 is going to be under. So I'm going to shade down here. And that's all I mean by shading. It can almost look like scribbling, and I'll show you how Delta Math shades, which is actually a pretty easy way to do it. If it only has x's, then it's going to be a vertical line. So you're going to go to -1 on the x-axis, put a point. Now, since this one has an equal to, it's going to be a solid boundary line. So there's my vertical boundary line. And then I'm going to shade the side that has values that are less than -1. So in this case, less than -1 is going to be to the left of that boundary line. So this is my shaded region. So those are your horizontal and your vertical. Those are the ones that only have one variable. If it has two variables, then we need to decide whether it's in standard form or slope-intercept form. This one, because y is by itself, is in slope-intercept form. So my slope is 2/1, and my y-intercept is actually 0 because there's nothing added on the end. So on your graph, you're going to go to 0. That's your y-intercept. And then your slope, you're going to go up to, since my slope is 2/1, right 1. So from the origin, I'm going to go up to right 1, put another point. Because this has a less than and doesn't have the equal to, I'm going to connect it with a dotted boundary line. Some people call it a dashed line. And then for my shading, since y is by itself and it's a less than, I'm going to shade underneath the line. So underneath the line is going to be right like this. So there is my shaded region and my dotted boundary line. This one is also in slope-intercept form, so I'm going to do this the same way. My slope is -3, so I'm going to write it as -3/1. My y-intercept is 6, so 0, 6. So on my graph, I'm going to go 0, 6, 1, 2, 3, 4, 5, 6, and put a point. And then since my slope is -3/1, I'm going to go down 3, right 1. So from that point, down 3, right 1, put my next point. This has an equal to, it's a greater than or equal to, so it's going to be a solid boundary line. And then since it's greater than, I'm going to shade above it. So I'm going to shade like this. So let me show you what delta math does, because I think it's nice to see it. So if we go to delta math, give me 1 second here. So delta math is going to do something like this. It's going to give you your inequality, and it's going to ask you to graph. So when you're doing this, you want to graph your y-intercept first. So you're going to go on your graph and put a y-intercept of -5. And then my slope is -3/4. So I'm going to go down 3, right 4, put another point. And the nice thing about this is it'll actually draw the graph for you. So again, I went down 3, right 4. And you have these options up here that say change line, change shade. So you have to decide, do I want it to be a solid line or do I want it to be a dotted line? If you hit change line, it'll make it dotted. If you hit change line again, it'll make it solid. Well, it doesn't have the equal to, so I'm going to change it to a dotted line. And then here's what shading will do. If you hit change shade, it's going to put it above. If you hit change shade again, it's going to put it below, and you can just toggle back and forth. Well, since this is a less than sign and y is by itself, we're going to shade underneath. So that's how you're going to do it on delta math. You're actually going to put your points that you want to plot. You're going to decide if you want your line to be dotted or solid. You're going to decide your shading. If you don't like what you chose, you can easily hit that button to toggle between. And then once you're comfortable with it, you're going to submit your answer. So I wanted you to see one like that. So let's go back to our work here. So here's one that's in standard form. So I want to talk about standard form and how we do these. So with standard form, you're going to do the cover-up method. So we're going to cover up my x's. So we're going to cover up my x's. And I'm going to write down what's left. So I have a -5y. When I do this, I just put an equal sign because I'm just finding the intercepts where it equals that value. So I can ignore the inequality for now. So I have y is -2. That's my y-intercept of -2. And then I'm going to do the same thing, but I'm going to cover up the y's. So let me cover up my y. So I'm going to get rid of this. So I've got 2x equals 10. Again, I'm going to ignore the inequality for now because I just want to know when it equals that value. So that gives me my y-intercept. So on my graph, I'm going to go to 0, -2 and put a point. And then I'm going to go to 5, 0, 1, 2, 3, 4, 5 and put a point. And I'm going to connect the dots with a solid boundary line because it has the or equal to. And for shading, this one's a little different. I'm actually going to use 0, 0 as my test point. So if I put 0, 0 in to this here and here, I'm going to get 0 minus 0. So I get 0 greater than or equal to 10. If that's a true statement, I want to shade where 0, 0 is. If it's not a true statement, then I want to shade the opposite side. 0 is not greater than 10, so I want to shade the opposite side. So I'm going to shade down here. So that's how you deal with a standard form one. Last one I want to show you is what if we combine the two lessons that we just did? What if we combine an absolute value graph with a shading and an inequality graph? So to do this one, I'm going to start by adding 1 to both sides because I want to get y by itself. So what I have here is I have an absolute value graph that shifts to the left 2 and 1 up. So on my graph, I'm going to go left 2, 1 up, and I'm going to put a point. That's the vertex of my absolute value graph. Now, since there's nothing in front of the absolute value, that means it opens up and it just has a slope of 1. So I'm going to go up 1, right 1, up 1, left 1, and I'm going to create my V graph. So my V graph is going to be dotted because it doesn't have the equal to. And then my shading, since this is a less than sign, I want to shade under the graph. So I'm going to shade down here. So I want to show you what that looks like as well. Again, on Delta Math, so if you want to go back to Delta Math and take a look at it, on Delta Math, you're going to get a variety of questions. You're going to get some like this one that are in standard form. You can decide if you want to rewrite it or leave it in that form to cover up method. You're going to get ones that are in slope-intercept form, and you always have that opportunity to change your line and change your shading to help you figure out what you're doing. And that's 2-8.